This is March 10th. This is an acid-base reaction. Remember OI, you're going to take the outsides, which is SO4, and it's going to go with the outside potassium. The OH is going to go with H. So I'm going to make on the product side H. Oh, I didn't think I picked. Come on. Really? Come on. H2O, which is HOH, plus a K, which is a plus 1. SO4 was a minus 2, so K2SO4. So I have to balance the charges as I go from side to side. After I balance it, I then need to balance the actual compounds, or the actual elements. So I've got 1 potassium, 2 potassium, so I'm going to put 2 here. I've got 2 OHs and 2 hydrogens, which will make 2 waters, and then I'm balanced. Now, identifying what is my acid and my base, my acid will give off hydrogen, and my base will take on hydroxide. And if I has hydroxide. So this one has hydroxide, this is my base. This one has hydrogen, it's my acid. Over here, this is water, so we know it's water. So this must be a salt. Because if I make water, then I probably have a stronger acid or base, and that'll make a salt. Okay? Now, saying I had a pH of 3, or molarity of 3.2 molar of this, and I wanted to find out the pH for all of this, and POH, and the concentration of the hydroxide. What I would do then is I would go and say, this, since it's a strong acid, I'm going to assume that my hydrogen concentration, and I'm going to be a little bit off because this is a diaprotic, it has 2 hydrogens it gives off. So I'm going to say it's going to be about 3.2 molar. Now, in saying that, then I can put it into minus the log of 3.2 and find my pH, which, if we do that real quickly, is what? Shouldn't be negative. Oh, okay, negative 0.5. I'm going to be really strong, that's why. Negative 0.5, one more. 1. Okay, so that will be my pH. So then if I take to find POH, I'm going to take 14 minus a minus 0.15, which is going to give me 14.15, right? And then to get the concentration of hydroxide, I just go minus, not minus, 10 to the minus POH, which is 10 to the minus 14.51. So my concentration of hydroxide is so this would be a strong acid. It's a very weak base. Now, all I did was the acid part of this. I didn't assume that I had added any hydroxide to it at this point. Okay. A salt, when I made the thing up here, when I get water, the other thing's a salt. Now, it can be an acidic salt or a basic salt or a neutral salt, but it's a salt. Okay?
Not water, then
if you have water, then you're going to have a salt. If you don't have water, then you might have a conjugate acid or a conjugate base, because that would be Brownsted-Lowry. Okay, so let's go over and announce. Right. The pH tells you the acid or base. Okay, so let's look at really quickly announcements. Maybe. Okay, announcements for today. Remember that if you're doing the Cub Scout thing, you're going to meet in my room during lunch today to figure out what we're doing. That is the last after school other than lab committee, so if you're not up on your lab committee, you need to do that. Extra credit options are still available here. Okay, all classes, late work must is due by Friday, March 18th. No late work will be accepted after that. That's next Friday. So if you've got stuff that you're working on, you want to get in, it needs to be in before next Friday. So going down here to AP, today we're going to do a lecture on buffers. So we're going to hold off going into lab a little bit. Today we're going to take a break, and then we're going to go into lab next time. So remember, we're doing after review sessions. Today after school is Thursday, so today after school, and then Monday during lunches. We have an extended take-home test. I'm extending it to the 18th, so finish it and do a good job, okay, because we're going to talk about buffers today and go over it a little bit more. So I've added the 2 labs. We're going to get to those as fast as we can next week. So we'll be working on a Monday and Wednesday, and then I won't be here on Friday. So you're going to have that time to pull those labs together, get them all in, get whatever things you need, so your lab notebook's real strong. Okay, don't forget the chemistry Olympiads. You got to go to one of them. 23rd is on Wednesday, so make sure that if you go, you have emailed before you go. And then we've got the chem test coming up on the 2nd. We will have an end of term test in class, multiple choice, and a couple of written problems. So be ready for that the last week of the term, the last A-Day. Not the last A-Day, the second to last A-Day, because the last A-Day will be going into the other stuff. Okay, we'll be correcting it. That's what we'll be doing the last A-Day. Yes, the last day of the term is an A-Day, which is dumb. You're not going to be here Wednesday? You won't be here the Thursday. That was the day that we'll be correcting. We'll be correcting that day, the test that we do. Okay, so let's go through some, I don't have notes for you, so you're going to have to take notes on your own today. So let's get through this real quickly. I'm going to move this over maybe. You can see this or not. Come on. There it goes, finally. It's just thinking about it. Okay, so maybe. The meeting of 2 personalities is like the contact between 2 chemical substances. If there's any reaction, both are transformed, by Carl Jung. This is a crystal of citric acid right here under polarized light. And we'll be working with citric acid in a little bit. So the big thing we're working about today is equilibrium in acid-base solutions and all about buffers. I think this is the buffer one, yes. So buffers. Any solution that contains an amount of both a weak acid and its conjugate base. Now, if it has a strong acid or a strong base, it's not considered necessarily a buffer. If it has its weak acid and a conjugate base, in other words, a salt, then it is considered a good buffer. So if it has any strong acids in it or bases, it's not considered a good buffer. Okay, it's highly resistant to change in pH. So we have buffers in our body to keep the pH of different parts of our body at certain pHs. If we didn't have that, we'd die. So a pH has to be close to the pKa of the weak acid. So characteristics of a buffer, and hopefully you've been going through your thumb drive textbook. A pH has to be close to the pH of the weak acid, or the pKa of the weak acid. So if you want a buffer at a pH of, say, 3.4, I want to look for an acid that has that pKa in order to make the buffer. That will be about that pH. Right. Right. So let's go forward here. We'll do a couple things. In a buffer, it contains 2 separate species. One that will attack acids or balance out acids, and one that will balance out bases. So one that can react with the H plus and one that will react with the OH minus, or the acid or the base. At equilibrium is about what happens after I start. So I'm not changing the amount overall. pH of a buffer is independent of the volume, so it doesn't matter how much I have. the pH is always the same, hopefully, of a buffer. And this is how you set it up. So the bottom number here, the moles of B minus, that's my salt. It's usually like a sodium or a potassium is what I add in there so I can get the base. The top is hydrogen, which means it's the acid. And in order to find my hydrogen concentration, so I can find pH, I'm going to take the Ka of that acid, times it by the moles of acid that I have, divided by the moles of base. Don't fall asleep, dude. Okay. All right, so that becomes a very important equation for you. We've got the Henderson-Hasselbalch. This is not on the AP exam. However, you can use it on the AP exam, but they don't give it to you. So if you know the Henderson-Hasselbalch equation right here, life becomes very much easier for you on the AP exam because you can use the Henderson-Hasselbalch equation to explain things very quickly rather than going about the long way of explaining it. This is an equation that I would highly, highly, highly suggest that you memorize, okay, and become very big friends with. Okay, you got it all written down? So, no, you didn't say anything. Be loud. So the Henderson-Hasselbalch is the one that you really want the most. So pKa plus log of the base divided by the concentration of the acid will give you pH. Yeah, that should have parentheses around it. Log of that fraction. Okay, we good? Okay. So here's some buffer systems. We've got the lactic acid and lactic ion buffer system in our body. That's when we work out really hard and we get sore muscles. We've sort of almost broken that buffer system. Okay, acetic acid. This is also one that is used. A lot of these are used in the body. So we have a weak acid and a weak base, and they go together, and we get a buffer system. What happens when a buffer system in the body is overwhelmed? We get hurt, or we have problems. So a runner that is in pain, exertion beyond the point at which the body can clear the lactic acid from the muscles causes pain. Okay? So how do I determine the concentration of hydrogen, or the pH? Come on. Whoa, and then it all comes up. So example 1, calculate the pH of a volume of 1 liter that contains 2.7 grams of cyanic acid and 2.54 grams of sodium cyanide. The Ka for cyanic acid is this. Now, if you've got the Henderson-Hasselbalch memorized, this becomes not a hard problem. If you don't, then you have to go through several things to get to it. Okay, so this is where I said it's really nice to know this for the AP exam because it goes very quickly if you know that. You can say, by Henderson-Hasselbalch, set it up, plug it in, and you got it. Okay, there are really 3 equilibrium systems involved here, and they're involved in every buffer. You've got the acid separating into hydrogen and its anion. You've got water separating into H and H+, and you've got the salt separating and going with water to make hydrogen cyanide and the hydroxide ion. So you want to choose the equilibrium system for the ionization of the weak acid. That gives the H+ directly, and then the pH. The ionization of water can be ignored since the concentration of H+ and OH are negligible compared to the same concentrations in the buffer system. They're usually 10 to the minus 7. Okay, so if there's 10 to the minus 7, as long as my buffer system has more moles than that, we're good. They can be ignored. Okay, so for the self-ionization of water, yes, but not in the others. Okay, so to write this, this is how we could do it. We could also write it with a Henderson-Hasselbalch. Okay, we can plug in what we've got. We got to change this to moles, of course, and moles, and we finally end up with now substituting it in. Okay, and then we can pH and we log it. So we would be a basic solution because we'd be above 7 for the buffer. That would be this. That would be the equation, or is to try and keep it right about 9. Okay. That's the Ka. It's a long way around. If I had just taken and plugged it into the Henderson-Hasselbalch, so this is, if I don't know the Henderson-Hasselbalch, this is the way I had to go around it. If I know the Henderson-Hasselbalch, I can just plug in. I think it's, I don't know if I did it on this one or not. Nope, I did not. It'll be another one. Okay, so we can go and see the pKa's for all this, so we can see that this one is going to be between the ammonium and the hydrochloride as far as a buffer system. Okay, so let's keep going. Let's do some more examples. So here I have an H2O4 minus and an HPO4 2 minus buffer with a pH of 7 that needs to be prepared. So I'm now responsible for preparing this buffer. Okay, I'm going to take the Ka of H2PO4 because I can see that both of those are going to be in that equation. And it is 6.2 times 10 to the minus 8. I need to figure out how many grams of each one I'm going to need to add to make this buffer. So you're going to actually be doing a lab like this where you have to prepare a buffer. So let's go through the steps. So I know that if I want a hydrogen concentration of a pH of 7, then my hydrogen concentration is 10 to the minus 7 molar. And I need to use the ionization constant expression of the weak acid to calculate the weak acid base conjugate ratio. So here's my thing again. So I'm working it through like I don't know the Henderson-Hasselbalch or anything like that. Okay. Rearrange and substitute in. So I'm going to rearrange it so I've got what ratio I need. Now remember, it doesn't matter the volume. I just need to have a ratio of what to what am I going to put in. So once I do that, I plug in hydrogen concentration, I plug in Ka, and I get a 1.6 ratio. That means for every 1 mole that I put in of the HPO4 2 minus, I'm going to put it in 1.6 that amount of the H2PO4 minus. Being really slow today, sorry. This means that for every mole of base, and I just said that, now calculate the mass of Na2HPO4 since 1 mole of that is needed. We also need 1 mole of this, which adds the salt in. So, got to get the other part of that in there, sorry. Come on. So the mass of this, 1 mole of it is going to be to 2 significant figures, 140. That's why the 2 dropped off, is I only had 2 significant figures. Okay, but I need 1.6 moles of the other one, so I'm going to times its mass of 1 mole by 1.6, and so I need 190 of it. Does it matter how much water I put it in? No, it does not matter how much water I put it in. So all I did is write the Ka for the expression and then rearranged it so I was getting a ratio of the base and the acid.
So you just find the Ka.
So basically I'm just taking the hydrogen concentration divided by Ka. So find the Ka, get the hydrogen concentration on the other side, and then I'm finding the ratio, whatever ratio that is. Okay, then once I found the ratio, then I just take and say, okay, I need 1 mole of what was on the bottom, and I need 1.6 moles of what was on the top, and I just times it by its molecular mass of that salt that I'm using. I could use sodium hydrogen phosphate, or I could use potassium hydrogen sulfate, or I could use any of the salts that had the hydrogen sulfate in it.
How do you know you can use 1 mole?
Because it was 1.6 moles back here. Go back here. 1.6 moles here. This one was on the top, this one was on the bottom. So this is like saying 1.6 divided by 1. So I'd need 1 of these for every 1.6 of these. Okay, we all right? Okay, so hopefully this will record. Therefore, to get a buffer of 7, I dissolve 140 grams of sodium hydrogen phosphate and 190 grams of the sodium dihydrogen phosphate into however much I want to add water-wise. So they dissolve. Now I'm going to be using distilled water, and the buffer isn't affected by this, how much water I have. Now if I take a part of that out, it will be affected. Okay? So we would have a buffer. Now, what happens when I add hydrogen and hydroxide to a buffer? This happens a lot on the AP exam where they say, okay, you've got your buffer made. Now I've added this much hydrogen. Now what's your pH? Kids go, midpoint through a titration. I've got to find a pH. So this is how you do it. We've done our titration curves. We sort of know what's going on here. If I'm adding H+, remember a buffer has 2 things that you've got in it. You've got something that will react with the acid and something will react with the base. So if I'm adding acid, it's going to react with the base side of it, right? Okay. When the H+ is added, the following reaction occurs. That's what's going to happen.
What?
It's just reacting with the base. It's just reacting with the base. So the hydrogen will react with the base. If I add hydroxide, it will react with the acid part. Okay, so I'm just adding hydrogen. It's going to react with the base part of that anion thing that I made. Now, it does 2 things to the buffer. It makes more acid. The concentration of the weak acid in the buffer system after adding the H+ is total number of moles plus the moles added. And it uses up conjugate base. So the reaction above shows that for every mole of H+ added, an equal amount of weak base reacts. Therefore, the concentration of weak base or conjugate acid after the H+ added is, right. Okay. So that tells me what my total moles of B- are. In order to find my new pH, I can throw it through the Henderson-Hasselbalch, or I can go back through the other way and figure out the long way. So I didn't do an actual calculation here for you, but the easiest way to find the new pH is now you've got the new moles of B- and you have the moles of HB, and if you've got your Henderson-Hasselbalch, it's really quickly, because it's pKa plus the ratio, the log of the ratio. Okay, so adding OH, you're doing the opposite. You are now using up some of your acid and making more base. Oh.
So it's just the opposite.
It's just the opposite. Guess I didn't have much more on that page. So if I add the OH, it's going to make more base. It's going to use up some of the acid. Okay? So it's directly opposite. Now, you got to be careful. The equivalence here is if I add something that has just 1 OH, then it's just going to use up, it's just going to put 1 OH in. But if I have something that has 2 OHs, like Ba parentheses OH2, then I'm going to have to do twice as much moles of OH added. Okay? So let's get to the point where we have limitations. So what happens when a buffer breaks, when you've added so much that it can't absorb anymore? Okay? So pain, yes. A large pH change that is added. So we've now hit the point where we've gone along on our pH curve and it's hit that thing where we go straight up. We've now broke the buffer and now it's now no longer the pH I want, it's higher or lower, depending on what I've added. Okay? So a buffer that has 0.1 moles of HB and 0.1 moles of B minus, for example, can only take up to 0.1 moles of either hydrogen or hydroxide, and then it breaks. Okay? It can only neutralize that much. If I add too much after that, then it can't handle that. That's like drinkers. Okay? If they drink too much before they become accustomed to it, till their body builds up a way to fix it, like usually when kids go off to college and do a stupid thing and do the binge drinking to get into the sorority or fraternities, they drink too much, their body hasn't been used to it, their body system buffer breaks, and they end up comatose in the emergency room, and they try and detox them fast enough, but a lot of times they don't make it.
That makes sense in terms of the titration, though, because like if the first one, since it was strong acid, strong base, 0.1 molar for both of them, it was like about equal
Amounts. Yep.
5 here and it's about 5 here.
Right. So they say if 0.2 moles of H plus is added, then 0.1 moles of H plus is unreacted. I reacted the 0.1 and I got left 0.1. Okay? And the resulting solution is reflected by, I used up all my buffer, but I have 0.1 moles of H plus left. So if I want to find the pH, I go minus log of 0.1, and I've got my new pH. I don't even worry about the buffer other than to say it's broken, and here's my new pH. So now I'm up here on the curve, or I'm down here on the curve. Okay? So here's an example. Let's go through this. A buffer is prepared mixing 3 grams of benzoic acid and 4.5 grams of sodium benzoate in 2 liters of water. The Ka for the benzoic acid is 6.6 times 10 to the minus 5. Calculate the pH for the buffer. So I can use the equilibrium system of the weak acid. I can set up my Ka, and I can solve for H plus. You see how I did that? All in one step. Okay, so all I've just done is rearrange Ka. Now we find the number of moles of weak acid and the conjugate base. So I figure out how many moles of the acid, benzoic acid, I've got. We've done this 1,000 times, grams to moles of the salt or the base. Then I plug it in to the equation that we did on the other side, the Ka equation rearranged, and we get concentration of hydrogen, right? From that, I can take the minus log of it and find the pH. You follow in steps? Okay. Why didn't I use the 2 liters? They're right on top of each other. They would cancel out. Okay. I know a lot of kids freak out over that. So because I've had them right on top of each other, they cancel out. So what happens if I take this buffer and now I add 10 milliliters of 0.1 molar HCl? So let's look back. I had 10 milliliters of 0.1 molar. 10 milliliters divided by 1,000 is 0.001, right? Times it by 0.1, how many moles do I have? 0.0001, right? How many moles did I have in here of the base that would react with the acid? I had this much. So I'm going to have plenty to cover that much acid being added. The buffer's not going to break, but it's going to change just a little bit. So let's go back here. First, I need to calculate how many are added. So, and I've got the number of H plus added. Since H plus has increased it, we add it to the number of moles of weak acid. Okay? And we take it away from the base. Okay, so I just added it to one, took it away from the other. Are we okay with that? So it was an acid. What? Because one is an acid and one is a base, so I'm adding it to my acid that I had in this container, and I'm taking it away from my base. It won't be the same amount because I'm adding it to my acid, but I'm taking it away from my base. Okay? All right, so we've done that. Now we calculate the pH of the buffer after. So now we've got our new concentrations. We throw it in there. We get our concentration of hydrogen minus the log of it, and we've got it. If I had the Henderson-Hasselbalch, I just plug it in and do all in one step, if I've remembered it. Okay, does that make sense? This one works fine. It's just one more step in the process instead of all in one. Okay, recall that before HCl was added, it was 4.28. So it's gone down just a little. So the buffer's holding its own. Okay, so what happens if I add 0.5 grams of NaOH? Well, change that to moles, right? It's the first thing to find out how many moles I'm adding. And it's 0.0125. That's a little bit more than what we had for our acid. So it increases the base side and decreases the acid side, right? So I do that really quickly. Say, plug it in, and I get my answer for my H+. So now my buffer has gone up a little bit. Remember, now it's up a little bit more because I added a lot more. It's still trying to keep it in the range. So calculate the pH of a buffer when 50 milliliters of 0.2 are added. So we're just going through it again. What were my steps? What do I need to do first? K is the same. So what's the first thing I need to do now? Find the number of moles. So I'm going to change milliliters to liters, times it by molarity, and I'm going to get moles. Okay? And since it's an acid, I'm going to add it to the acid, and I'm going to subtract it from the base. So I get my 0.1 mole. There's not enough weak acid. I only had 0.0313. If I take 0.1 minus 0.033, I've got 0.0687 that's not reacted with the base. There's no base to counteract it. So then I just take that, go minus the log of it, because the buffer has been destroyed. You usually get 1 point for saying that in the AP exam. The buffer has been destroyed, or the buffer has been used up, or the buffer is no longer active or valid. Okay?
So when there's too much hydrogen
or too much hydroxide, the buffer will break. That's what we call it, buffer breaking or buffer destroyed. Okay, the concentration of H plus is, we got to make sure that we add the total amount of liters here, because this does make a difference here. So we added 50 milliliters. We've got to add that to our original 2 before we can come up with a new molarity. And then with our new molarity, we do minus the log, and we've got our new pH. So because there was such a big change, we do have to make that 50 milliliters is a lot to add. And that'll affect the concentration. Okay? All right, so that is a drop from the original 4.28 to 1.47. So it really bombed out. So we've been using acid-base indicators. The nature of the acid base is basically a weak acid, weak base. It's sort of like a buffer thing. What does it do? It changes colors depending on the pH and its pKa. So depending on where it's at, it will give you a bunch of different things. It's derived from a weak acid, and depending on how much we have, it shifts the reaction. So it's sort of a Le Chatelier thing, going back and forth. So if I have more acid, it's one way. If I have more base, it's another. So it is a visual thing. Okay? The principal species is the color that you observe of your acid. When I shift it, and it becomes the IN that I'm seeing, which is the base. The color in between is an intermediate. So basically all that you need to know, I'm going through this fast because you really don't need to know all this. The color is dependent on the pKa of your indicator. Okay, whatever the pH of the indicator is, that pKa is my intermediate, or point that is important. So we can actually boil red cabbage juice and get a really good indicator. It will go red in acid, and it will go yellow in base. So we've done titrations. I'm going to go through this really fast. We've done the strong acid, strong base, where we neutralize and get a salt and water, and we've got that titration curve. Yep, we're familiar with that. Okay. We're going to be doing other titration curves where we do a strong acid, weak base, a weak base, strong acid, and a weak acid, weak base, which would be a buffer. Okay. We get a salt and water and a strong acid, strong base. Some indicators that we can use. Now they have asked what indicator you can use. We have used phenolphthalein for most of the ones we're using back there. That one changes at a pH of 9. But if you end up with lower than 9, that you have a weak base titrated with a strong acid, you might not get up to 9. Okay, so you've got to use some other indicators. Some of them are really easy to see. They go from clear to pink, like phenolphthalein. Bromothiamyl blue goes from yellow to blue, and you have a green in between, so you've got to decide when is blue and when is not. Methyl red goes from yellow to red, so you've got an orange in between. Okay. The starting point, this is where they usually have you find pH. The starting point, when no titrant has been added, halfway to the equivalence point, and at the equivalence point. So here's an example. If I have 25 milliliters of 0.2 molar perchloric acid, strong or weak acid? Strong acid. It's one of our 4 oxy acids. Is titrated with KOH, strong or weak? That's a strong base, part of the tetras pattern. Okay. Okay, so for our acids, we go HNO3, H2SO4, HClO4, and HClO3. Those are our strong oxy acids. Then we start HCl, HBr, HI. Those are our binary acids that are strong. Over here, we come to sort of like a tetras pattern. Lithium, sodium, potassium hydroxide, slide over, calcium, strontium, and barium hydroxide. Those are the strong ones. Everything else is considered weak, with the exception of the hydroxides in the first 2 columns. Okay, they sometimes are considered more moderate. The ones that we didn't count are more strong. Okay, so if no titrant has been added, then I'm just worried about the 25 milliliters of the when 0 titrant has been added, 4 KOH is added. All we're worried about is our acid. So we're just worried about this much of this. Okay? We just take this, which is the concentration of the hydrogen, and go minus the log, and we've got the pH. That's our beginning. We haven't added any OH. Okay? Then, halfway to the equivalence point, we're also going to do a graph, and you'll see what happens here. But basically, okay, we've got a volume, and we've got H+, we've got a molarity. We know how many moles are there. From the OH minus, we know its molarity. The moles, to determine how many moles of OH have to be added to reach the half titration or half neutralization, we take the moles of H+, and what do you think we're going to do? How do we get halfway there? Yeah, if I want to get halfway through the titration, I'm going to need half as many moles, right? Okay, so we cut it in half. That's not too hard, right? And then we say, okay, we can determine the volume by going moles divided by molarity, gives us the liters that we're going to be. So now we put the acid and the base together, we get this reaction, which is strong acid, strong base. Reacting 0.5 moles with 0.025 moles of OH means that the OH gets all used up, and the number of H+ left over is 0.0025, right? So I've just used half of it up. That's all, it's basically all that's saying. I've used half of the H+ up. So the total volume of the mixture, if I used half of it up, this is the part that everybody gets messed up on the APT exam, and they mess it up and lose at least 2 points. I'm telling you right now. They forget to add the 2 volumes together, because you got to have moles over total volume for molarity. So add those two together. Now I've got moles, now I've got liters. Take moles. So here's total moles that are left with H plus. This is how much volume I had to add, how much I already had, gives me this much volume. Because they said I added 0.025 liters up here. Figured that out already. Okay? All right. So going forward, so H plus in the solution to the halfway point, the molarity becomes this. Minus the log of it, I've got the concentration at pH. Okay? Still pretty low. Just a little statue that's been damaged by acid rain. So what happens at the equivalience point? Well, they're equal to each other, right? If it's a strong acid, strong base, I should know the pH. What's it going to be? 7. Okay? So strong acid, strong base at the equivalence point is always 7. Any other thing, if I don't have a strong acid and a strong base, the equivalence point can go up if I have a strong base, weak acid, or it can go down if I have a weak base, strong acid. So the equivalence point is based on what two things I'm putting together. Okay? Okay, we are going to be going into some titrations like this, and I'm going to have you do examples or do so you actually see what's going on. This one is a strong base with, weak base with a strong acid. Strong base would be up closer to 14. This one's down lower. You'll notice that it goes down and it becomes lower. My equivalence point here is at 5. It's no longer at 7. That's because the acid is stronger than the base. Okay? Come on. That's what I just said. Okay, conjugate acid and water. What are the types of indicators that can be used here? We have to find one in that range. And what they'll usually do is they'll give you a table of possible indicators. And you need to know that if I have a strong acid with a weak base, it's got to be lower than 7. I've got to have a pH indicator that changes lower than 7. If I have a strong base, weak acid, it's going to change above 7, so I need to have an indicator that's above 7. Phenolphthalein is probably a good one. Okay? In general, titration of a weak base with strong acid, the indicator should be change color on the acid side of 7. So there's a big list of all the different kinds. They might give you something like that and say, okay, which one would be the best one to use for this titration? Okay? Now, if you look at this one right here, it's really hard to see color change, right? So you've got to know, is it a color change that's going to be really easy to see? That's clear to yellow. That one's a hard one to see too when you're in lab trying to see clear to yellow, because you can see that little area in here that's really. Why is thymo blue red? Because up here it also changes again. Okay, so there's some indicators that change it more than one place. A universal indicator has several of these indicators put into one solution. So you get several color changes at different pHs. Yep, that's why I said don't put anything you're going to eat. Put whatever you would eat onto the pH paper so you're not contaminating. Okay, when no titrant has been added, you do the same thing. Titrant is always as strong as the acid. We did it already. Half neutralization. Half of the weak base has been converted into conjugate base, into the reaction. We get equal amounts of base and acid substituting into the equation. If we get equal amounts, then it's equal to the concentration of the hydroxide. And pH can easily be found. Now, be careful on this, because what I see a lot when I've been grading is that kids will take the minus log of the POH and forget that it's POH, not pH, and stop. Remember that if you have concentration of OH, if you take the log of it, minus the log of it, it's POH. You got to subtract it from 14, and then you get pH. Okay, one next step. Okay, at neutralization, okay, remember here that the molarity of the weak acid formed is determined by taking the number of moles of weak base, which is equal to the number of moles of conjugate acid formed, and dividing it by the total volume of solution. Volume of the weak base plus the volume of the strong acid titrate. We talked about that with the buffer. Whenever you're working weak acid, weak base, you're basically working in buffer things that we talked about before. So here's an example. I'd like to be at least able to go through the example. So consider the titration of sodium cyanide with HCl. Okay, sodium cyanide, strong, weak, what is it? What is it? Is it an acid? Is it a base? It's a base. How did you determine it was a base? It's going to be Cn minus, right? Sodium's a spectator, it's going to go away, right? Don't get caught up in the sodium. Sodium's a spectator, it's going to go away, not be affected. With HCl, what is that? Strong acid, right? So calculate the pH before no titrate has been added. So before the titration, the weak base CN minus ionizes in water according to the equation. So we're going to get cyanic acid and hydroxide. So the equilibrium constant expression is lovely, right? Okay, so we're going to use the table again to get the KB if we've got a KB chart. If not, if they gave us KA, we have to do that. We're also going to need to use ICE. Now this is before they came out with ICE. They had this PowerPoint, but I reached back and grabbed it. So this would be ICE. This is how they used to have us do it. Okay, so I know some change is going to happen, and some of it's going to go to hydroxide, and some of it's going to go to HCN minus. So as I do that, I set it up, and what did we decide about the minus X on the bottom? We have to assume close to 0, or assume very small, right? Okay, it needs to be less than 5% of what the total thing is. So we're going to look it up, the KB, or you'd be given it, and we've got this, and we can solve for X. And I just said it's very, very small compared to this. We get the end here. We do a check, make sure it's less than 5%. It is. Okay, and we could go on. So it's well under 5%. The assumption's okay. And we do, since this is the 0.001 is our OH concentration, we go minus the log of that. That would give us POH. Subtracted from 14, we got pH, which is basic, which it should be. If I end up with something that's acidic, then I know something's wrong. So if I try to stop here and I'm working with a base, I know I didn't finish. Okay? Initial, change, and equilibrium. So the first row here is equilibrium, middle row, change, and the bottom row at equilibrium. So what is my concentration going to be at equilibrium?
Oh, so I is like the first thing.
Initial. Then change, what's changing, and then finally what's going to end up. Okay? So at half neutralization for this, we've got the KB, we've got the KB, we take minus the log of that, and that's our POH. Okay, at the equivalence point, we can do the same kind of thing. Okay, so next time when you come, okay, I did give you some extra time for that test, so make sure that if you don't understand it, you're coming in and getting help. The ones that are later on are more clear than the ones at the first. I think a couple of the ones at the first were a little, I should have taken them out, but I used somebody else's test.
You just taught us how to do that stuff.
Okay, so, all right. Have fun. Have a good weekend. Get caught up on everything, please.